Today I'm going to be discussing the maximum entropy versus Bayesian approach to analyze flow networks. So we're going to begin by going over the methodologies or basis of the two methods. So the maximum entropy method is a method to assign or update probability distribution to describe a system which is not completely specified, potentially an undetermined set of equations. The probability distributions obtained from the MaxEnt method only contain information from the prior and the constraints, and the constraints can incorporate physical laws, and the inferred distribution can be interpreted as the most probable distribution which represents the system. Okay, how to actually go about using the method is you define the variables of which you are interested in, construct a relative entropy function over those variables, identify the constraints, maximize the entropy function subject to those constraints, and then, if desired, extract moments of the quantities of interest such as means and variances. The basis of the method can either be taken from a combinatorial approach or an axiomatic approach. The combinatorial approach is given here, which shows that the distributions that you get from the maximum entropy method the distribution can be realized in the greatest number of ways. Alternatively, you can choose these three axioms and you will get the same distribution as you would through the other method. Okay, Bayesian inference, on the other hand, is also used to update a prior to a posterior, but you're using data, so that's actual measurements. Okay, before you start any Bayesian analysis, you need to choose your prior and also your likelihood functions. Then to analyze the data, to analyze the data or update your prior distribution, you evaluate your data within the likelihood function multiplied by your prior, and then you normalize it and you get your posterior, and then you can use that posterior as your prior for the next piece of data. And Bayes' rule just comes from the product rule of probability and also marginalization, as shown here. All right, to go about analyzing flow networks, what we can do is we can define, to begin with, that we are interested in our external flow rate represented with theta and our internal flow rate represented as q. We can note Bayes' rule. Now, because, as I discovered with the maximum entropy method, Bayes' method also has the same issue, that if you change your network representation, you will get a different inference. So to get around that problem, I have set this up so that we are now going to analyze a subset of the flow variables rather than all of them. And that subset is capital X. And to be able to do this, you need to be able to find the variables which are not included in the probability distribution as a function of the variables which are, and that's given by X with a bar over the top. And what I've got down the bottom left-hand corner is a matrix which you could choose equations from in order to be able to form that variable v to find the relationship. That capital C is for coefficients for conservation of mass. The next one is for loop laws. The capital F is for any flows that you happen to know or have data about. And T is for any potential differences between any 2 points. And the K is the resistance to flow. Alright, so we're going to look at the likelihood functions here for imposing each of the constraints. So the first one, it's just a normal distribution. I've taken the log of the normal distribution. And also the first two constraints, conservation of mass and loop laws, they're actually likelihood functions, but they're taken as delta functions because I am fairly confident we're not going to have any variation about conservation of mass, whereas my measurements of flow rates or potential differences, because I'm measuring them, there could be some uncertainty, and therefore they are Gaussians. And this value here is just a diagonal matrix saying the number of observations which I happen to have of a potential difference or of a flow. And the splitting up which is done here is only because I'm working on a subset of the flows. If I was working on all the flows, I would just be using the straight C and W matrix and so on. Alright, so if I take my likelihood functions, I multiply them by my prior, which I had chosen to be a Gaussian, I then get this posterior distribution, and I've tried to make it fairly compact by letting O equal this and now a covariance or inverse covariance in this case, and also my observations for, so that's the mean of my observations for flow rates and potential differences. And the other two are obviously zero because I am looking at a conservation law. Alright, so if I go through and do the algebra, I end up getting that my mean and covariance with the Bayesian method of my posterior are these, and a bit of algebraic rearrangement, which I'm doing, so I'm going to compare it with the MaxEnt method, and also to be able to deal with delta functions as well, because if you look in this form, you'll notice that in here, some of the terms in that S matrix have a variance of 0 because they're a delta function, and trying to find an inverse of a function or a matrix with zeros in it is a bit problematic. So the algebraic rearrangement ensures that I've worked out how to take that inverse correctly. Okay, the maximum entropy approach. So again, I go through to find my variables of interest, and in this case, because I'm looking at including constraints of which I'm not certain about it, so I'm using measurements rather than accurate values, I'm going to define my probability distribution over the variables of interest, the flow rates within the network, and also my observed flow rates and my observed potential differences. Okay, so next stage, I define my relative entropy function, which is just a standard entropy function. My first constraint is a normalization constraint, and so on. I've got conservation of mass, loop laws, and flow rates and potential differences. And if I go through and maximize my entropy function using the method of Lagrange multipliers, I end up getting a probability distribution which looks like this. of which, if I decide my prior to be a Gaussian as set here. Now my prior includes my prior over the flow rates within my system, which gives you the top line, and also the measured value of flow rates and also potential differences. And I'm incorporating that information also into the prior. And potentially on these measured flow rates, I may have more than one observation at the same location, which would mean that these matrices such as the F matrix that you would have seen earlier will just have two rows of the same value with different values according to the observation that you took, which will have some mean and some variance. And I'm also, for the sake of working through this, going to be working again in the log space, and everything becomes proportional to that. And what I'm going to do now is find my Lagrange multipliers, which I can take my probability distribution, substitute into my constraint functions in order to find what they are going to come out of. At the end of it, I end up getting a mean of my inferred distribution looking like this, and my variance is the same as my prior variance. Alright, so here I have what the Bayesian mean looks like, and here I have what the MaxEnt mean looks like, and they end up actually being equivalent, because where this 0 appears here are where the delta functions were in the Bayesian methodology, which means that they cancel out. And these values here are the uncertainty on the measurements. So it ends up that both the maximetry method and the Bayesian method give the same means, but their covariances are different. So the Bayesian maximetry methods rest on different theoretical foundations. They can take observations and update a prior relief to a posterior. Now, there's one large advantage of the MaxEnt method over the Bayesian method, in that in the MaxEnt method, I incorporate the interactions between variables within the Lagrange multipliers. Within the Bayes method, those interactions go into the covariance matrix. Not having any covariances is a major advantage, because what you can do is you can integrate each dimension as a one-dimensional integral and then multiply those integrals together to get what your final posterior PDF is going to be. Whereas if you were to work with the Bayesian method, you have to treat it jointly, and trying to do a large dimensional integration is going to take a huge amount more computational effort than what it is going to take to do a large number of one-dimensional integrals. Thank you.